Okay, I think today is going to be quite an important lecture. It's going to tie into like everything we know so far, and tie to the way projects are built, what we call data science pipeline. Okay? By the way, the midterm results are in. There are 5 of you who are actually in big trouble in terms of the results, but the rest seem to be okay, hanging on all right. Okay, there are about 4 or 5 of you who are borderline survival. Okay, right. Okay, so let's get started. First of all, let me just go and share screen. Now, okay, let me just spend about 5 minutes or so, sort of like giving you guys a recall of what we have been covering, right? So, from the beginning of the class, I think as far back as lecture 1, we were talking about the foundation concept. That was when really we put the concept about big data, data analytics, machine learning, artificial intelligence, everything sort of like together, okay? Put them together in context. So I gave you guys all the definition here, and this is in your interactive textbook, right? The concept, again, about learning, about machine. Machine is something that does some tasks for us, but it's one of those things where it's not a machine that's ready to work out of the box. You have to give it the first task, which is to learn the problem first before it does another task which is useful for us. Okay, so that's the concept. We tied this thing with the concept of data analytics. So basically, there's this picture that maybe I can show you. Let's see this. Okay. This is for presentation. I think I'm making on Friday. But there's this picture. Oops. There's a picture that I thought would be a good tie-in. Yeah, these 4 things that are really important about the concept of artificial intelligence, the concept of machine learning, the concept of quantitative models. At the end of the day, you're building the tools. The tools is at the bottom of the data analytics, right? The data analytics is what allows you to analyze inside of data. So data information into better decision making, better decision into better decision. Whatever. Yeah, that's really the whole building part. So you can think of it as the whole class here, from the 15 period or so that we are together. It's about studying what it means to build data analytical tools. Yeah, tools to analyze data. Now, the tools to analyze data from the first class, we talk about sometimes if you just make the visualization, interactive visualization, a good graph, it just gives you the insight right away, right? So visualization is good enough to give you insight, good enough to analyze, gives you the analysis of the data. But a lot of time you have to build some kind of model that learns insight from the data, extract insight from the data. Okay? So all these tools that give you analysis, I would put under the umbrella of quantitative models. Okay? Any kind of models that basically look at your data and then give you some kind of computation, to assess, do some prediction, do some kind of clustering, groupings, whatnot, whatever. Yeah. Now the top part is the machine learning. It's what we focus on. But of course, you didn't have to focus on this, right? Because last year you already studied statistical model. So statistical model is also part of the arsenal. Yeah? Except it's an arsenal that you presumably have already learned. Statistical tools like linear regression, logistic regression, so forth. You've done that. So this year we are focusing not on those. but on the new set of tools. That is the tool that is basically built on machine learning. Okay? Machine learning in turn is inspired by artificial intelligence. Okay? And to bring the whole thing back full circle, the validity of the whole enterprise, starting with artificial intelligence, to say that yes, we can do better, we get better insight if we perform quantitative analysis based on machine learning models. Machine learning models, which are in turn inspired by the 1950s, research based back in the 1950s, trying to get insight into how human beings learn, what it means to be intelligent, what it means to be human-like. Yeah, so that's what we want. So anyway, oops, as stop as shared window is closed. Okay, so let's go back to our note. Okay, so we cover sort of like perspective, where we stand, what's the object of all this in, right? And then there are some background items that that we cover. We cover a little bit of the mathematical or computational programming, sort of scientific computation. I think this was covered in 2 weeks ago, I think, last Monday, I think, okay? And again, this is something that a lot of it is doable in Python, but it's a lot more powerful and a lot more concise to do it with Mathematica. So so this is sort of like the tools, the basic tools. Now, the underlying and week 1 we covered this thing, right? So I'm gonna close that, the visualization tools. We covered the data mining. Okay, this is the more or less review chapter, because you already presumably learned this last year, right? In the statistical method. Again, we covered the background of linear algebra and elementary calculus. Some of it would have been covered in high school even, right? But this is something that you need to go forward with machine learning. Now, so we go to machine learning, and as I mentioned, machine learning comes in 3 flavors, roughly speaking. Okay, it's gonna expand a little bit, I think, in the future. But right now we say, and I think this was in a midterm exam as well, probably. I think the 3 paradigms of machine learning, right? Unsupervised, supervised, and reinforcement. This is like how baby learns, how human being learns, right? Unsupervised is trying to organize the relationship of objects in space, group them together. Dad with one thing, and mom with maybe with being fed, or dad with doing homework or something like that, or this kind of thing that babies start to make automatic association. But if the baby is learning things like this is supposed to be called an orange and not an apple, you have direct immediate feedback. That's supervised learning. And if the baby has certain behavior over time, like cries a lot, and if he cries a lot, he gets positive response, he gets what he wants, then he becomes spoiled, right? But if he cries a lot and he doesn't get positive response, but if he's, acts rationally, or maybe just politely asks for things and he does get it, so it becomes reinforced, that positive behavior. So that's kind of like reinforcement learning. So the 3 paradigms are very important in machine learning. But for this class, I'm excluding the reinforcement learning because it's a lot more relevant to things like robotics and so forth. For data analysis, it's going to come down to these 2 types, unsupervised and supervised. Okay? Now, unsupervised, we covered the two principal approach, the 2 principal modes of analysis. One is sort of like clustering, where things together, right? Group things together, things that are close together in some kind of vector space, right? So this is something that has become relevant to the nominal group, again, the nominal team that's doing the analysis of the suicide rate for different countries. And I said, well, in order to say to study peer country, you don't just say you take Thailand and the country next to it is Burma or Myanmar. Okay, that is close geographically, but it's not close in terms of socioeconomic variable. Okay, what's close to Thailand in terms of socioeconomic variable? That would be like clustering analysis. Okay, then the second mode of unsupervised learning fall under the umbrella of the rubric of dimensionality reduction. This is to help you visualize, first of all. So you can say that countries are close together when you consider 30 socioeconomic variable, but you can't visualize them. Okay, so how can we do this? How can we represent Thailand on a two-dimensional graph, represent Chile on a two-dimensional graph in such a way that if Thailand and Chile are close together in a 30-dimensional space, they are also close together in a two-dimensional space. Yeah, so this is to preserve the closeness, but in a lower dimension. Okay, and I mentioned that this is used for visualization, but also it's used for information extraction. Sometimes you don't reduce from 30 dimension to 2. Sometimes you reduce from 3,000 variable down to 30. You still cannot plot it, right? But it's an extract. It's more concise. It's more information rich set of variables that you will be using for something else. Okay. Now, so today is about not about unsupervised learning. Okay, because I think from looking at the project, most of the projects here will focus on using supervised learning tools. Okay? So today is supervised learning day 2. We already had day 1 before the summer, before the midterm exam. Okay, so right now let's go back a little bit. And you remember these interactive tools that I show. Let me go back a little bit. Regression line fit as a right. Okay, let me go to this. Regression. Oops. Where are we? Right? Okay, you guys remember these interactive tools? Right? We talked about that. Okay. Now, this is a good thing to keep like as a visual reminder, because last year you already learned linear regression problem. You learned linear regression problem. And linear regression problem, once again, is trying to find the best fit that set of data. Okay? Trying to find the best fit of data. So it is a supervised learning problem because you can tell right away whether or not the model is doing good or bad. Okay? Because it gives you right away the prediction of the fitting error. Okay? But last year you didn't learn it as a machine learning problem. You learned it as the statistical fit. The reason is that if the data falls into this line, this line here, to minimize the error, okay, calculus gives you a very good closed form solution for the best fit. Okay? And that's called ordinary least square. So under statistics, you just take this data, put in the formula, and you get the perfect fit. You get the perfect line fit. There's no machine learning involved. So one step thing. Okay? Calculus guarantees that it's the minimum error you are going to get by fitting that ordinary least square line. But with machine learning, okay, to make the simple problem hard, what you have is some kind of a free parameter, a line that has certain parameter. Depends on where that parameter is. It may fit well, it may fit worse, right? And the machine learning, like a child learning, is trying to make prediction or make a Y estimate, and it's given immediate feedback as to whether or not the error is good. Okay, lots of error or minimum error. So the game is to try to move the parameter. So this is sort of like the parameter. You're trying to move this parameter slowly, bit by bit, until you get to the line that fits really well. Okay. And for this problem, I think this one. Okay. Oops. It's getting close. It's not quite there yet. And I think I have to move one more step. Okay. Right. So you can see this is like an error service. Now, this is silly to do with machine learning because you already have a closed form formula, right? But imagine that the problem is different. The problem is to fit some other data set, which is not linear, right? Now, in theory, if this is a function you see a lot, mathematician can also derive a closed form solution for it as well, right? But of course, machine learning is powerful because it doesn't work on limited form. You don't have to say it's this shape, it's that shape, it's linear shape, it is parabolic, it is cubic shape. Okay, this is just an example, I'm making it up. But in real life, it could be any shape. So mathematicians will not be able to figure ahead of time what kind of relationship it is. So the mathematician gives you instead a machine learning engine that allows you to fit arbitrary shape. Okay, and that's what machine learning is trying to do. Okay? That's what supervised learning is trying to do. Now, so I'm gonna close this. It's a save and go back to the original. Okay. Now, with supervised learning, there are basically two problems that we are going to focus on. One is what we saw just now, like a regression, right? You can say that if the output is a number in this case would be something like something from equal scale or ratio scale, right? Or occasionally from ordinal scale. But if it's classification, the output would be the name of the object, right? Which if you make it numerical, it's just gonna give you nominal scale. 1 for boy, 0 for girl. But 1 is not better than 2. Sorry, 1 is not better than 0. Boy is not better than girl. Cat is 2, dog is 3, but cat is not better than dog, or dog is not better than cat. So you only say that 2 is different from 3, okay? So the two problems that we are dealing with is regression and classification. Now, from the project, remember we discussed the project, you guys paid attention to your friend, right? I already said that most of the projects here are supervised learning problems. Okay, let me ask you, are most of the supervised learning problems regression problems or classification problems from your project, from your friend's project? If you're paying attention to what your friends were doing, are most of the problems, do they fall under regression, like numerical estimate of something, or do you get some kind of classification? Okay, why would you say that? Well, let's go through them. We can go through them. For example, the suicide rate estimation, that's definitely regression, right? The Bitcoin, I don't know who, I don't think we have Bitcoin project anymore, right? Yeah. Now, what about other projects? The project that look at the picture, right? Then it's something, first of all, there's two stages. There's a classification of what do you see in the picture. And then there's a classification of from based on what's in the picture, are you gonna get positive lights or negative lights, right? But you can also make it a regression problem in terms of estimating the degree of positive, right? For example, if you think about it, if you count, let's say you count the number of positive response, right? And you divide by negative response or something like that. Okay, the ratio, the odd of positive to negative, that's kind of numerical. So that could be considered a regression problem as well. Yeah. The football problem, okay, where you try to find the best combination of players, okay, But before you get the best combination of players, you have to learn which combination beats which combination. We'll talk about it today, but it's going to be a classification of sort. The classification results in A beats B versus B beats A. Okay? So in other words, we can sort of like input characteristic of team 1 and team 2, and your output is a classification, whether or not the outcome would be the first team beats the second team or the other way around. Okay, so it is certainly a classification, but you can also think of it, what if you want to think of it as a relative odds, sort of like relative strength of team A versus team B, right? So it could be some kind of scoring, some kind of continuous scale scoring, that if it's a higher number, then it increases the probability that team A will beat team B. So in that case, it's more like a regression. Okay? So it's not always fixed. It's not always clear that you have to do one or the other. Yeah? Ultimately, it looks like if you have a regression problem, it's probably best. If you could, because it gives you sort of like detail, rate, and so forth. But sometimes you can't. So it's a classification. And some problem definitely is classification, like recognizing cats and dogs. Yeah, it's not scoring catness or dogness, right? You're not saying, okay, let's create a score for cat and score for dog and try to predict the value of the catness. You don't do that sort of thing. So it's most likely for cat and dog object recognition, it is classification. Yeah, and classification is quite interesting. It's quite interesting, and it is basically even though I did mention to you the statistical method and machine learning method, they kind of complement one another. Yeah, they also have different area where they're strong. Definitely, regression analysis or classical statistics don't work with classification very well. Okay, tend to work with regression. With machine learning, it works well on both. Okay, so I like that in that sense, I would like to say that machine learning is more powerful than statistical, because it tends, at least with respect to classification problem. Okay, you really never do any statistical classification. It's rarely done nowadays. It's doable, it's rarely done. Now, classification, you will notice that there are two separation that I make the case here. One is called binary, so yes and no, 1 or 0, A or B, and the other one is multi-class. Yeah? So yes or no would be, is this a bad person? Is this a bad debt? Okay, is this car car insurance, is it gonna be activated? Is there gonna be an accident within the year? Yes or no? Yes or no? Right? But you can also do like multi-class classification. That would be definitely the problem that you have with recognizing object in the picture, right? Because you're not saying, is there a cat in the picture? That's a yes or no, right? But you have multi-class because it could be a cat, it could be a dog. You want to know that, right? And yours is a little bit even more complicated because you don't just have one object. You can have more than one object, right? Yeah. So multi-class classification would be something like, of all the 10 types of animals possible, which animal is it? So that's a 10 class, right? What else has 10 class? Well, number has 10 class. And today we're going to talk about digit recognition. 0, 1, 2, 3, handwritten digits. Yeah, so that's multi-class. Now, so, yeah, you understand that we're talking about data analytics that require more than just visualization, require some kind of quantitative models. The quantitative models we're talking about would not be statistical model, which is what we learned last year, but this is learning machine learning based model, right? Machine learning based models are very good at doing 3 kinds of learning: supervised, unsupervised, and reinforcement. We're dropping out reinforcement learning for this class. Yeah, it has a little bit less relevant for data analysis. So supervised learning and unsupervised learning for this class, I think only the nominal field, the suicide project, will be trying to put countries that are close together, and possibly the football team project, when you try to say that the characteristics are similar. It's like unsupervised clustering of player, right? You can do that, the cobweb clustering. Most of the problem in the project will be supervised learning. Okay? And on the supervised learning side, it's some problem can be formulated as classification, some be formulated as regression. But I think anyway, my sense is a lot of it is on classification, a lot more. Okay, with the exception of maybe the suicide rate prediction. Okay, so we're going to do supervised learning classification today. Okay. Now we already started with what? We already started with, again, this is not machine learning, this is simple statistics, right? This is simple statistics. But why do I want to start here? Okay. Sometimes I kind of lose sight or lose track of whether or not I've made certain comments already. But have you heard me making the comment that a logistic regression is equivalent to one neuron? Have you heard that? Okay. So this is the basis for that, right? Again, to review, and I'm gonna need a picture for that. This is a neuron, right? Human neuron. It has an axon. You guys see this? Wait. Let's go to picture of internet then. Hold on. How about neuron? Okay, and I'm searching over the image. Okay, very good. Okay, now let me share this picture on Zoom. Okay. New share there. Right? You guys see this picture? Let's make it bigger. Okay. Right. What's happening here? What's happening here? Each neuron, okay, each neuron has what's called dendrites. Dendrites are sort of like incoming. Okay, it's receiving signal from the dendrites. It's receiving signal on the dendrites. Okay, so basically it's getting neural chemical signal across the synapses. Never mind. Basically from other neuron. So this thing gets some signal. This thing gets some signal. This branch gets some signal from here, from here, from here, from here, from here. Right. So maybe this dendrite here is connected to one neuron. This dendrite is connected to another one. This one is connected to another one, and so forth. So it's basically getting information simultaneously, well, not simultaneously, but almost simultaneously from all these connected neurons. Okay, so let's say there are 100 neurons connected to it. Okay? Each incoming neuron would send a signal or not. Okay, based on that signal, if you get a signal, and based on the conductivity of this dendrite, it then accumulates the signal strength. And if all the signal strength adds up together is strong enough, the neuron is going to get excited. Okay, and it's going to send its own signal. Okay? Once it sends its own signal, the signal travels down the axon and it sends to other neurons it is connected to. So you can imagine that there are M neurons coming in, and then it goes out to N neuron, right? So maybe 100 neurons send signal coming in. If you add the signals together and it's strong enough, then it fires and it sends a signal to another 100 neurons. Okay? This is one neuron, right? Now, of course, if I have 100 of these, and each signal has the conductivity of the channel, it's like a weighted sum, right? Right? It's like x1 times w1 plus x2 times w2 plus x3 times w3 plus x4 plus x100 times w100. You guys see that? The weighted signal? Okay? So this is equivalent to all the signal coming in, and if it's strong enough, it sends an outward going signal. So this is the sigmoid function, right? So if the signal is strong enough, it sends out an outgoing signal. Okay. Now, what good is that? What good is that? Well, if I have a hypothetical neuron that has only two dendrites, okay, two dendrites, okay. One dendrite is connected to this axis. One dendrite is connected to that axis, right? Based on the coefficient of dendrite 1 and dendrite 2, I can actually draw a straight line that separates one group of this class from another, right? So that's what this thing does. And let me go to this. Multi-layer processing. That's where we are. Now, this is what you should see. Okay, you guys see on your screen, right? So instead of having a neuron that has 10 or 100 incoming dendrites, I'm just making an artificial neuron that has two dendrites. One dendrite is called X, one dendrite is called Y. Okay, and based on that coming in, if the signal is strong enough, when I multiply, then it gets output signal of 1. Okay, now this here is one neuron. So I can change the slope here, right? I can change the slope here. So basically, the relative strength of the dendrite, right? The connectivity from the neuron aligns the yes or no. So what's happening here is that one neuron can separate, in this case, two-dimension space into two groups. Just positive or negative, right? And that's exactly what a logistic regression model does. It gives you a partition of data set into two groups. One group does not excite, so it gets a value of 0. One group gets a value of 1. That's it. And based on the orientation of the weights, it decides how am I going to separate, right? So if I want to separate this from that, I use certain set of weight, W1 and W2, or dendrite's strength, right? And if I change it, it becomes like this. So I can separate any two groups in this part. The problem is with one neuron, the limitation of one neuron, and by implication, by extension, the limitation of one logistic regression analysis is that it can only separate with a straight edge. Okay? The function itself looks like it has a curve, but actually the separation is linear. When you look from the both, the separation is linear. So that's the problem. That's why classification with logistic regression, with traditional method, is not powerful at all. Right? It's not powerful at all. How many times I could have one problem in maybe 100 dimension that is separated exactly by this kind of a straight edge? That's how you want. This is how you want. But this is what, you know, say the technology was 10, 20 years ago for banking. Okay, to separate say good debt from bad debt, you have something like income, education. And the higher the income, the higher education, the less likely you are to default. Like that. So you make a straight line. Okay? But you definitely can make a curve. Now, this here, I hope you play with it when I gave you this to play with, is to have two neurons add together. It's as if you have two, what is it, regressions together. Yeah? Once you have two, you can crisscross. And when you crisscross, you get something more intricate. You get some pattern like this. Right? You get some pattern like this. So it could be something like, I'm not just separating left from right, but I'm separating left from right, top and bottom. So I'm going to separate the northeast from southwest, which you could not do with just one neuron. You cannot do with here. What is it? But you have to do with neural network. But of course, this is only two neurons, right? In real life, how many neurons do we have in a typical neural network? Well, in an application, you can have 1,000 neurons easily. So it's going to give you a very complex curvature. Okay? Literally, I can draw a line that goes, very weakly by using combination of that. Now, again, because mathematicians don't know the problem ahead of time and you're going to be facing how many neurons you're going to use, they don't derive the perfect formula for the neuron weights. So you leave it to the algorithm to adjust slowly, W1, W2, W3, W4. Slowly, to get the best fit. And that's what this means. Okay? So the first paradigm that you learn, okay, the first paradigm that you learn today, or not today, but is this thing called multi-layer perceptron. Maybe I should give you another picture. Multi-layer perceptron. Okay, and it looks like this. It looks like this. Okay. So each little circle you see there represent like one artificial neuron. Okay. Again, they're making it simple. So in this case, it has 5 different neurons. Now, the way it's done, let's take this picture. Let's take this picture. Let's take this one. Let's take one. Okay. This one, in terms of biological brain, what do you see? You see that there are 3 neurons. Each of them has 4 dendrites in the first layer. And then you have another layer of 3 more neurons that has 3 dendrites. Okay? But each of them has 1 axon. Okay? And then you add up all together, and presumably there's another neuron over there. So you can have 1 neuron here. So the picture we saw just now, the picture that I simulate just now, it looks complicated from just 2 of these, right? But now you can have 3 of these. But you don't just have 1 layer, you can have 2 layers. You can have 3 layers, 4 layers. Okay? And this is what we call multi-layer perceptron. Okay? Each neuron is called perceptron, and you have layers of them, and you have multi-layers. So it's called multi-layer perceptron. It's easy enough. Fine. Okay. Now let's go back to our thing. Okay. You can play with 3 neurons later if you like, but Now let's get to how we build the problem, how we build the neural engine. Okay, and this is really the crux of what we're doing today here, machine learning model pipeline. Okay. Now, before I go on, I want to make sure we did cover non-neural supervised learning technique, right? Like decision tree. Yeah, decision tree. Okay, good. So, in your project, I think one team stood out because wanted to use auto-regressive moving average model, which I don't think that's going to work very well. Okay, but for the rest of you, I think are going to be using some variation of multi-layer perceptron. Okay. Now, let's get something clear. In a human brain, okay, it is possible that the neurons are not organized in layers. Okay? It's just a whole bunch of neurons, okay, that are connected. Maybe some of them are stacked up in layers. Like maybe you have a neuron that from a visual field, that's one layer goes to the next, but it's not guaranteed. So the neuron in real life looks like this. Okay? Then like this, then this goes to here, this goes to here, that goes to here, this comes back here. It's all kind of jumbled together. Okay? It's all jumbled. But for your problem, which is to learn the input to predict y from x, you have to go from x to y. Okay? And the way it's done, without loss of generality, is to organize it into layers. Okay? So all the neural network model you will learn will be based on multi-layer perceptron as the basic architecture. Okay, let me say that again. Human brains have neurons that are connected to any kind of pattern. Okay, this can evolve over time. You were a baby, some connections get lost as you grew up and so forth. This is biological. It's a little bit messy. In our case, it's not messy. In our case, neurons line up like soldiers, you know, like in a form of parade. Neuron. One layer. Another layer of neuron, and you have this kind of sequence going from the first layer, send the signal to the second send to the third send to the fourth, and so forth. Okay? Next week, I will introduce occasion where you kind of feedback to itself. It's called recurrent neural network. So you get this layer 1 to layer 2, and layer 2 come back to feed onto itself, something like that. That's possible as well. But most of the time, you always think of layer of neurons, and most of the time they are fully connected. In other words, if you have 5 neurons in this layer, you have 10 neurons in this layer. Each of the 5 neurons here is connected to all 10 of that layer. The second one is connected to another 10, to the same 10. It's fully connected, right? It's fully connected. Now, is that true in real life? Of course not. Not all the neurons are organized into layers, and even if they're organized into layers, they don't always connect, fully connected, right? But in computational algorithm, it's fully connected. Okay? So you always see this picture. The picture will be like this. This guy is connected to every guy. This guy is connected to every guy. And from this perspective of this guy, gets signal from everyone below him, send signal to everyone above him, yeah, that sort of thing, right? But there's no cross. You don't send signal in between your layers. Yeah, it sounds a bit silly, but that's the way it works. Okay, it's ours in our and it is. Yeah, right. Now there are other architectures that are fancier, like maybe you have signal here to here, but don't worry about it. Okay. For all practical purposes, you can say pretty much for the rest of your professional life, all the neural networks you see will be in layers and layers and layers. So one layer next. Yeah. Now, the fancy version will have something else added to it. Okay? But you will always have multi-layer perceptron. It's not just a full fashioned neural network. It is basically the base So all the past project, I think, you know, the football, the predicting, yeah, from image to response and all kind of stuff. Kind of forgetting a few projects here, but will be multi-layer perceptron. Okay, so with that in mind, let's get busy. Okay, let's get busy. Now, here's the thing. Here's the thing. Let me go to. I'm going to cover 3 machine learning problem. Okay, the iris data is 1. The iris data is 1. LeNet on MNIST is another one. And finally, the one called predicting uveitis. Okay, maybe I would do this. Put this one first. Yeah, maybe something like this. The reason I leave MNIST last is because it's going to be relevant to at least certainly your project here, your object recognition. Okay. Okay. So you guys ready? All right. Now let me give you. Let me go to this slide that. That I used earlier, and let me go to this slide. Okay. Now, okay, good. Okay. These two, did you see the links, right? And I'll give you the links in the line group again. A very good animation of multi-layer perceptron and how multi-layer perceptron works. Okay, let's look at the top one. So the top one is neural network by the 3 blue one round. That's a picture here. Okay, it gives you a very good animation, shows you how the multi-layer perceptron works. The second one is called CNN, convolutional neural network. I'll talk about it later. But anyway, I just want you to know that this is something I'm going to give for you to look at after class. It's very good. It's, you know, the animation is wonderful. Yeah. Okay. Okay. Let's now. This is where we come. So far I've talked a little bit about you know, multi-layer perceptron and saying that it can make any kind of complicated mapping from X to Y, complicated to Z. But now we're going to get down to actually building. Okay? And this is what we call building a supervised machine learning pipeline. For some reason, the word is blocked. Okay? The reason we call pipeline is a little bit like plumbing. Okay? It's the beginning to the end. The starting from data all the way to like water source to a pipe. Okay? What do you need to do? So let's assume, okay? I'm going to assume that you have already formulated the problem. And that formulated problem, by discussing the code, is going to take the form of supervised learning. Okay, so I think for supervised learning, okay, what is the first step? The first step, of course, is the data preparation. Data preparation, right? The data preparation means you have to harvest, you have to keep the data, download, and whatnot. Okay? Now, that is only this line. Harvesting, cleansing, and sometimes it's called munching, so that manipulating the data. Now, the pre-processing is the next step. This is to say that, okay, now we are going to make the data in the form that the machine learning algorithm will recognize. In other words, the machine learning algorithm, if it is supervised machine learning, it knows that it's expecting input and output as a pair. Okay? So it's not expecting a table of bunch of numbers. It's expecting series of I/O pairs. use that word a lot, I/O pair. Okay? Input, output pair. Okay? Now, in Mathematica, which I'll show you later, it looks like this. It's a list, so that's a curly bracket, right? Or, let's say your function is y is equal to 3x plus 2. Okay? If x is 1, what's y? 5, right? So it's going to say 1 has to map to 5. If x is equal to 3, y is going to be 11. If x is minus 5, right, y is going to be minus 13. Okay. Now, this is the form that Mathematica can understand as an input-output pair. Okay. Again, you have a list of input-output pair. Okay. In this case, input is 1, output is 5, input is 3, output is 11, input is minus 5, output is minus 13. Okay. Right. Now, let's go to example. So I'm kind of like slowly working new share. Okay. So, what was the first step? The first step is to harvest the data, right? To get the data, clean the data. Now, fortunately, this is an example data, so it's already clean. I don't have to go through the step of looking at eliminating NaN and whatnot and so forth, all right? So this is a curated data. So data train, okay? You guys see that? Let me make it a bit bigger. For some reason, when I go to Zoom, these things slow down as well. Weird. Okay. The training data is equal to resource data. Okay. Resource data. This is a function that basically looks up archive data. Okay. So this is not universal. So a lot of times you have something like import CSV or something like that. But in this case, I'm looking at the example data. So the resource data named MNIST. Okay. What's MNIST? MNIST is the handwritten digit. Handwritten digit, okay? Character. And what do I want? It already separates training data from testing data. Okay, we have to talk about training versus testing data. But in this case, they already separated for us, so it's quite easy. Okay, fine. So let's download that. So we got this data set. Okay? Now, I call random sample from data train. Okay? And I draw 5 of them. See? This is what it means by the data is already in an I/O pair format. It's a list, right? In the open curly bracket, close curly bracket, it's a list. It's a list of I/O. In this case, it's not from number to number. It's actually from, this is actually an image file. Okay? To you, it looks like a number, but to a machine, this is not a number. This is a picture. This picture is pixelated 29 by 29. In this, I think it's 29 pixel by 28 pixel by 28 pixel. I think, yeah, I think it's 28 pixel by 28 pixel, right? Pixelated, digitized, handwritten number. So the data puts this. Now, this is something that's very clever about Mathematica. You can work with object in its original form. You don't have to translate it first. You say, well, this is a picture, and it knows that it is a picture. And it knows it is a pixelated data. So let's look at this guy. All right? Now, fundamentally, what is it, guys? If you have 28 by 28 pixels, right? What is 684 something? Okay, you have 684 pixels. The value goes from 0, meaning black, to 1. That's what it means. Okay, so Mathematica is smart enough to say, well, this is actually a list. Internally, it is a matrix, 28 by 28, or 684 numbers from 0 to 1. 1 being white, 0 being black. If it's 0.5, it is gray. So for this pixel, it is close to 0. This pixel is 1, and so forth, right? Okay. So that is what I mean by the second part of the pipeline. It's not only you get the data, you know what input, what output, you prepare it in the format that your algorithm can understand. Okay. Now, so this, in this case, now Python may have a different way of doing things, but I think the easiest way that I found is this. Basically, a list of A points to B. A points to B, A points to B, A points to B, right? Yeah. Except here I'm just drawing a random number of 5. Okay. There's a whole bunch of them. There's a whole bunch of them. There's like 1,000 of them in this data set. Okay. In fact, how do you know? Well, let's see, length of data train. Okay, 60,000, right? 60,000. There are actually not the 5 that I showed you. There are 60,000 examples. That's to train the model. Now, once you train it, you test it on the data test. And let me see how many examples is that. You have 10,000. Okay? So you train on 60,000 and you test on the 10,000 you haven't seen. If you test on the thing you've seen, it's kind of cheating a little, right? Right. Now, here's where I want you to pay very close attention. And somebody raised this question before class. Okay. You have to get the data into input, output, right? And a lot of time, the data will not be separate to training and test. So sometimes I use this function in Mathematica called take about 80% of the data and use it as train and then 20% test. So this is how you read the function. It says, take the length of the data. Okay, let's say you have 1,000 data point, 1,000 data point, multiply by 0.8, so that gets you 800, right? Floor, that's basically just round down, okay? Because sometimes you don't get even integer. So this will give you the number 800. The function say, take the data that's already in the IO form, take the first 800, call it data train, and the other 200, call it the data test. Now, did I have to do that for the MNIST? No, I did, because for that MNIST data, they already separated to 60,000 to 10,000. Okay? So you have the data, okay? You have the data, it's separate to training and testing. This is called training and testing, validation I'll talk about later. Then you build the machine learning engine. By building, you have to create a neural network that has an initialized weight. In other words, it's like a regression equation that doesn't have coefficient yet. It's an empty coefficient. Okay? Based on the data, you have to then find out the values. Then you run the experiment, you draw a conclusion, and so forth. Now, in Mathematica, it's very easy. If you want to do classification, this is what you do. You take the training set, which is already into IO form. You call the function called classify, and then you say the method is neural network. This is like when you don't know of anything, you just make it automatic. with Mathematica, again, it's scientific computing. So you can go as deep as you like, but they also assume that before you know anything, let's just automate things. Okay? And in this case, it's saying that, okay, automatically give me some neural network. Now, neural network, remember, is a layer of neurons, right? Right? So when I say neural network, it's just a generic term. I haven't said how many layers, how many neurons in the first layer, and what that function from 0 to 1, that mapping function, there's some variation in as well. I can specify. So all this can be specified by data science, by the experimenter. But the Mathematica is saying, for now, there's some kind of default architecture that tends to work well. So all you say is say, quote unquote, give me some neural network. Yeah? That is a way of saying that I want to use multi-layer perceptron, generic looking multi-layer perceptron. In fact, it's even more clever than that. You guys remember, right? We can do non-neural machine learning as well, like random forest. We can do decision tree, gradient boosting. So instead of putting neural network, I could say something like method is random forest. Yeah. Even more clever than that, I can leave this thing out altogether. Just don't type with method. Then it becomes automatic. What it's going to do for the problem that's not too difficult, it's going to try all the algorithms or a few algorithms, give you the one that it thinks is best. So it's kind of automating this. Now, do I use this? Yes. Do I use it professionally? At the beginning, yes. To get something going, to get some results and get some initial analysis. But when I'm going to do a proper professional experiment, I will be specifying the learning, the algorithm, and all kind of things myself. Okay? But this is something that's easy. Okay? And then based on that, you measure, oops, sorry. Based on that, you do a test. It's called classification measurement test against the data set. So this is how it's done. So this is the whole pipeline. The whole pipeline from data to the algorithm to the result of the experiment. Then you draw a conclusion, and then you make some kind of visualization, all that stuff. That I leave it up to you. Okay. So that's the overall pipeline. Yeah, machine learning pipeline. Okay, so let's go look at some now. On next page, we're going to talk about how to build the machine learning engine. Okay, but now I'm going to say let's just go to our okay. So let's start with iris data. Let's start with iris data. Okay, iris data. Again, we have time to go into 3 pipelines. If you take this pipeline as a template, I think you'll be in good shape. Okay, so this is actual example. Okay, actual example. Remember last time I draw this picture? So that you have this method of math, right? And this is your problem and the data, right? And when you read a paper, you read all of this. And then you use method to apply to your problem to your data. Well, this is that kind of exercise. I'm going to show you the whole thing that is for the iris data. Iris data. Yeah, okay. So, what's an iris? Let's go to, what's an iris? Iris. That's what an iris looks like. Okay, that's what an iris. Yeah. Now, what is a flower? Sorry, that's a bit silly. Okay. Normally, when you look at a rose or something, okay, petal versus sepal. Whoops. Let's just look at this picture. I don't want to go to the page. Okay, fine. Right. Let's look at the flower, right? The flower has petals. That's the pretty colorful thing that you see. Yeah? The sepal is the creamy thing that covers the bud, right? That covers the bud. Now, what happened in most flowers? What happened in most flower is that when it blooms, this thing sort of like disappears. You don't see it. It becomes something very small. Like in a rose, if you look at a rose, you see the petal. You don't see the sepal. It's too small. Yeah. Now, iris is different. Iris is one of those things where even though the petal has already, bloomed, the flower has already bloomed, you see a lot of big petals, the sepal is still big. So you see both, right? Yeah, so this is the petal and this is sepal. So it's a bit funny, right? In this case, the sepal is bigger than the petal. Yeah. Normally, the sepal doesn't have any color, it's just green. It just sort of like covers the bud in the beginning. Now for iris, so you get basically two sets of three propellers, right? Petal and sepal like this. Right? Now, never mind. Just say you're interested in flowers. Okay? Let's say you're interested in flowers. Well, it turns out that iris comes in three varieties. Yeah, three varieties. So, when you want to recognize which variety it is it a binary classification? Of course not, because it has three parts, right? So that's what the problem is. Okay? Now, what is the information? How do you recognize different? Let's say you never do this approach. I want you to be able to identify different types of iris. Well, you can perhaps use what kind of information? Color, shape, right? Well, in this data set, they have 6 measurements. There's the length, right? The length of the sepal and the width of the sepal. Sorry, not 6, 4. And there's the length of the petal, width of the sepal. Nothing to do with color. Nothing to do with color. Let's see if it works. Now, obviously, I'm using this as an example so it works. But in real life, this is what you see. When you come to a problem, this is what you see. You have to think, how am I going to be able to distinguish one type of flower from the next? Is it going to be color, the weight, smell, and so forth, right? There is one project that might be using spectral information. The defect function. Okay? So in that case, it's not looking at the width or the height or something, right? It's not looking at the scale measurement, but it's looking at the color. Well, in this case, the long and short of it is, you can definitely forget about the color. Yeah, they have done the study. They say the color doesn't really, you don't really need to do the color. So what do you have? What do you have? You have this. Now, this is the column name, as it were. Sepal length, sepal width, petal length, petal width, and species. Again, there are 3 species, right? Okay. For example, this guy is, I think, 5 centimeters sepal long, 3 wide. The petal is 1.4 centimeter long and 0.2 centimeter wide, and it's a setosa. Okay. Basically, you have 3 varieties. Now, in this case, they make it so that the first 50 is setosa. Setosa is A. Okay. The other 50 is versicolor, and the other 50 is Virginica. Okay. It's 3 colors, right? Sorry, 3 varieties, 3 species. Now, never mind, because I know that if I do the take drop 80% and 20%, it's not going to work, right? Because they order. Yeah. So if I take the last 20%, it's always going to be Virginica. So what I do is, in this case, let's say I take 35, 15, 35, 15, 35, 15. That makes sense, right? So I'm trading on 70% and testing on 30%. Okay? So I take the first 35, the second 35 from 50 to 85, and the third 35 from 100 to 135 as my trading. Okay? So that's basically it. Okay, train and test. So that's what this means. It just say I'm taking the data from the 36 sample to 50 sample. Now, here's an interesting thing. Remember, I told you that you wanted to build a model, and you don't know which model you want to. You have no preference. Okay, so in reality, you might try them all. Neural network, logistic regression, decision tree, random forest, support vector machine, naive based nearest neighbor. Okay. Most of the time, now the mathematics is not just going to give you the one with the best accuracy. It's actually going to give you a balance, the one that has high accuracy but not too many parameters. Yeah, because if you have a lot of parameters, it might overfit or something like that. So it's trying to, if you have the same level of accuracy, it's always going to give you the one that has less number of parameters. Yeah, so it's kind of like a heuristic thing. Anyway, so these are the classifier method I want to try. Yeah. Now, in reality, I can just say, I don't care. I just leave it automatic. But in this case, I make this. So now, I want you to look at this structure. I'm creating a classifier, right? But I'm not just making one classifier now. I'm trying all 10 of them. So it's a classifier on the training data and the method. But the method is applied to all this. So I'm not just building one model. I'm building 9 models, right? So there it is. 3-second pass, it's training something, it's training gradient boosted tree, it's training something. This is live, by the way. This is okay, so it's 1, 2 seconds, 3 seconds, 4 seconds, done. Okay. Random forest, 2 seconds, 3 seconds, done. Gradient boosted tree, 2 seconds, 3 seconds, done. Logistic regression, 2 seconds, 3 seconds, done. Support vector machine, 2 seconds, 3 seconds, 4 seconds, done. And the last one is the last one. 5 seconds, 6 seconds, 7. Neural network takes a bit long. 10 seconds, 11 seconds, 12 seconds, 13, 14, 15, 16, 17, 18, 20. Okay, 22 seconds to train a neural network. So it takes a bit longer. They are all trained. Okay. So now, okay. For example, what's the first one? The first one is automatic. Now, this is where I like to do in real life, in a professional work. I let the machine choose first, automatically, and it tells me the degree of complication. If I ask the model to choose freely, and it gives me logistic regression. That tells me that the mapping is not that complicated. Okay, so let's see what it gives you. Gradient boosted tree. Well, gradient boosted tree is kind of like a fancier version of random forest or decision tree. It's sort of like a sequence of trees. Now the second one I chose nearest neighbor. The third one, blah blah blah. Yeah. Now I'm gonna measure the performance. Right? I'm gonna measure the performance. So this is all trained. Now I did this before class just to make sure that it didn't. So what's the first guy? The first guy has, whoa, perfect accuracy. The second guy has 97% accuracy. Again, it's not a difficult problem. 97.8% accuracy, 97.8. This is a toy problem, so don't worry, it's gonna be easy. This one has perfect accuracy. Logistic regression has perfect accuracy, right? So what this problem is telling me is that this problem is trivial. You can use literally logistic regression, and I told you it's not powerful at all, and it's going to give you very good accuracy already. Okay, so again, I'm not using this problem because it's complicated. I'm using it because it's simple. Now, obviously, I can show. Oops. You guys remember the confusion table, right? Let's just look at this. Actual cost, Sentosa, prediction, Sentosa, 50%, 15 example. So it's getting very good accuracy, right? Sentosa, 15, predict all 15 of them. How many? Versicolor, 15. How many predicted? Versicolor, 15. How many Virginica? 15. Predicted 14 of them as Virginica. There's only one error, versicolor. Okay, something like that. Okay, so it's close enough so that this is rounded down, so it's get 100% accuracy. It means it has 1 out of 150 error, so that gets rounded down to 0. Okay. Now logistic regression gets perfect, literally perfect. So this is basically how you would do model building. Yeah, you have to keep narrowing down. What are you doing? Supervised learning. What are you doing? Classification. How are you doing it? Well, in this case, I don't know. I'll try them all, or I let Mathematica pick for me. It turns out the problem is so trivial that Mathematica picks gradient boosting or logistic regression, and it's giving me a perfect prediction. Okay? It is. That's why it's called a toy problem. You know that you can get perfect accuracy. Okay. Now let's go to the second set. And this is more interesting because this one is not guaranteed. Okay, I went to this website called biogps.org. Data set, gene expression in inflammatory diseases. Okay, I'll just give you one sentence. Any of you guys from I guess in high school thought about going to medical or biological area? Well, anyway, the central tenet, the central dogma of molecular biology works like this. You know about genes, right? You know about genes, okay? Right. Well, it's actually not two-step. You think gene determines who you are, or the shape, or what you become. Actually, it's a two-step process. The gene gives you the instruction for building protein. Okay? Proteins are like little molecules. Okay? The gene, right? The gene is an instruction. That instruction gives you a sequence of amino acids that curl up your protein. Basically. Okay? And if it curls up into a shape that looks like this, then it's a protein that does a cutting function. If it it curls up into a shape that looks like a hammer, it becomes a protein that does the pounding. If it curls up into a shape that looks like a protein that fits into a virus, then it becomes an antibody. It locks onto the virus. Okay? So the shape determines the function. Okay? The gene tells you what the protein to make. No, sorry. The gene tells you the recipe for making protein. But the choice of protein to make does not depend on just the gene. It depends on what's called gene expression process. It's like you have a recipe book. Okay? You have a recipe book for making omelet, for making pie, for making noodles. Okay? That's the gene. That's the gene. But the gene expression is another process that tells you when to make omelet, when to make noodle, when to make pie. That's why, if you think about it, you know about butterflies, right? Butterflies, when it was a baby, it didn't look like a butterfly, right? It's just a little worm called pupa, right? Okay. They have exactly the same gene. Because one is the child, one is the adult. But they don't look alike because when it's a baby, the recipe that is used to make baby. The recipe is all there in the gene. Okay? The recipe is all there in the gene. It just depends on where you read. Read this bit, you make baby worm, baby pupa, right? And then you read another bit, and then you make butterfly. But it's the same gene. So it's from genetic material to expression. That expression then determines the form. That expression determines the form. Now, with a human genome project, they take all your genes and map it all out. That's like all the recipe you have. But it does not tell you what is going to happen. So if you don't exercise well, if you smoke, if you sleep late, maybe it will not produce the healthy protein. Even though you can, it will produce a bad protein. And ultimately, that's what cancer also does. The cancer not only has the womb corrupted, the gene is corrupted, but it also expresses certain antigens. Yeah? So the gene expression process. So anyway, the point is, this is gene expression data. So it's not genetic data, but it's gene expression data. But the summary is very easy. It comes to this: the disease state, the sex, age, sex, uveatus status. Basically, it's predicting uveatus. Uveatus is eye infection kind of thing, right? It's a medical condition. It's based on this characteristic. Okay. So anyway, so the data. Okay, you're trying to predict the disease state. So I download this data. Okay, I download it. Look at it. Okay. Now this function I haven't shown you, but basically it's doing this. If the person has this thing called sarcoidosis, is 0. I think 0 is male or female in this case. So this sample, sarcoidosis female, 59 years old, has uveatus. 1 week has uveatus. Okay. So let's do this. Let's say random sample XY. Let's say 5 people. Yeah. Okay. So you have control group. Control group meaning no disease. Female 59, no uveitis. Okay, so she's okay. This person, sarcoidosis, female 41, has disease. Control group, female 24, no disease. Control group, female 49 years old, no disease. This group has what's called, I don't know what it is, axial spondylotrophy. It's a male. Okay, so this is basically what's meaningful in gene expression. Okay, to me, doesn't mean anything, but that's what gene expression, I guess, results in. Yeah. So this is basically the prediction. Now, I don't have to turn this into word or into ordinal, into nominal scale, because mathematically it automatically does that. Okay, so this is what I did. I take drop, and this is the excerpt I use in the slide, right? Take about 80% as my training data, right? And then I do this. I say, let's classify. Now again, this one, I'm not even telling what the model is going to be. So it's going to pick something. It's going to pick something that it makes sense. Right? So this is my classifier. I'm learning it in real time. Okay. Yeah. Right now. Okay. Oops. It's running. Okay, good. It's giving a logistic regression, decision tree. See, she's trying a few things. Random forest. Yeah, it's trying nearest neighbor. It's trying that as well. It's trying nearest neighbor. It's going to take a while. Okay. Can you see that? This is their time. It's trying nearest neighbor. It's trading nearest neighbor. Right? It's trading example views, 48,000, blah, 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 49 seconds. Nearest neighbor apparently takes a hits. Okay, now it moves on. It goes on to something else. It uses what else does it use? 1 minute has passed. It's tried. How many algorithms did it try so far? 3 or 4? That's it. Nearest neighbors seems not doing very well. It gets stuck. So let it run a little bit. Eventually, it's going to stop. It's going to stop. I can also run this on GPU, which should give it a little bit faster. But anyway, okay. So it's not doing very well here. This guy, this new. So it's going to try something else, I think. Okay. So this is the same thing as when I did the method. It's the same thing as saying method automatically come out with the method. Okay. It's not stuck. For some reason, 2 minutes has passed and nothing has come. Okay. Well, anyway, it's gonna finish. Oh, nearest neighbor is really no good. Let's stop this. Okay. Well, this is embarrassing. Why is it's not? It seems to be stuck, right? This is the current loss. Okay, it's using 48,000. Nearest neighbor. You know what a nearest neighbor identifier is, right? It's using something similar to cluster analysis, where it measures the distance. It's saying that you're a boy, you're a girl, you're a boy, and somebody here sits here, right? So who's this person close to? Closer to this guy, and maybe close to that. So based on some kind of averaging, you say, well, it's likely to be a boy, because it makes you a boy. Okay. So it's not really all that clever. It's called nearest neighbor. Okay? You are similar. If you are close in X, you should be close in Y. That's what it is. Okay? I don't know why this is stuck. Don't like this. I don't like this. Something is weird. Something like me. Let's abort. Yeah. Let's do method neural network. Yeah, decision tree. Say gradient boosted tree. Let's limit it to that, I think. Yeah. Don't know why. Before the class, I just ran it. It ran okay. It tends to hang a little bit when I go to Zoom. I don't know why. It has nothing to do with it. Okay. Gradient boosted 3. That's a bit slow. That's weird. Okay, but with not when I ran before class, it's really quick. Maybe something to do with going to school. I don't know. Weird. I can't tell you why. But anyway, it shouldn't take minutes. It should take seconds. Okay. Now, once I get it right, once I get it, it does the classification. Now this is earlier we saw. Not only do I give the prediction, I can also ask for how sure the model is. So my classifier for this person, this is somebody comes in. Give this example. Sarcoidosis, male, 50-year-old. Instead of just saying, does this person have uveitis? I actually ask for probability. So again, remember, some problems can be thought of as classification. Some problem can be thought of as regression. So giving a probability is a little bit like regression because it's giving you numerical value. Okay? It's kind of estimating value, except that's bounded between 0 and 1. Okay? So in this case, the person who is male, 50 years old, has sarcoidosis, okay, has an 80% probability of not having uveitis. Okay? And 20% probability of having uveitis. Oh, okay. Yeah, when I did earlier, by the way, when I did it earlier, the preferred model that Mathematica gave me was a decision tree. Yeah, the basic simple decision tree. Okay. So based on that, it's going to give you some kind of confusion matrix plot. Okay. Once again, I apologize. I don't know why it's not running, but it did before class. Okay. So because it's a binary classification, not only can we do confusion matrix plot, you can also do ROC, receiver operating characteristic curve. Okay. So for your problem, okay, for your problem, if you have binary classification, I would expect from your project to output not only confusion matrix, but also the ROC curve. Right? Because the ROC curve is the effect of the false positive and true positive. Right? Basically, if you say nobody is positive, you don't have false positive, but you also have no true positive. If you say everybody is positive, then you don't have false negative. You don't have you have perfect true positive, but you also have false positive as well. The point is you want to have true positive faster than false positive. So this ROC curve is going to be bulging. Okay? So the more bulging you have, the better. Have we talked about break? You guys want a break? Okay, let's make 5 minutes break. Yeah, good idea. I want to find out why this thing is being held up. It's a bit weird.